to The Last Fireflies, a radical climate podcast with an Eastern European focus.
Hey folks, we are back with another Doomscroll episode. Oh no, it's Infospill actually, but anyway, I'm Robbie and I'm together with M today.
Yeah, hi everyone. I'm here to ask questions about things.
Cool. And we will continue our discussion about accelerated warming that we started in the last episode and try to delve a bit into what is causing this warming. So just to give like a short recap, last time we talked about the fact that in the last decades, before 2010, the global temperature was going up with a kind of a steady rate of 0.18 degrees per decade. But now in the last 10 years maybe, it's kind of been jumping all around temperature. And it seems to be going up with a new trend of 0.3 degrees per decade, maybe more. And that's a worrying fact because depending on what's the explanation for it, it might be the case that, after this kind of transient, chaotic period of a few years passes, the temperature stabilizes to this new trend, this higher trend. And if that is the case, then all of the scenarios of the IPCC will need to be revised upwards. So the same emissions will lead to higher temperature rise than we have in the IPCC's reports. And so, it's a really, really huge deal that has real implications also for policy, but also it should have for our activism, right? And so today, as I said, we will try to progress a bit with understanding where this accelerated warming is coming from. So the first observation is that if you plot a map of global temperatures, the first thing you observe is that over the land, over the continents, there's nothing really extreme happening. And the huge warming is actually coming from the oceans, and in particular from the North Atlantic and the North Pacific oceans, where the temperature rise, the temperature anomaly, as we call it, is really, really extreme. So it has to do with the oceans. This is the first clue. And to get another clue about it, we need to look at Earth's albedo, which has been steadily decreasing in the last maybe 20 years.
The Earth's albedo, not Earth's libido, just to be clear.
Yeah, no, it's albedo, not libido. And I guess Earth's libido has also been steadily decreasing.
For sure.
From what we've been doing to it. But so the albedo is the reflectivity of the Earth. How much of the energy from the sun it reflects back to space without being absorbed. So if the albedo is decreasing, it means that the Earth has been steadily absorbing more energy each year for the last, let's say, 15 years. So let's think a little bit about what could affect the albedo. First of all, we think of ice. Ice is white. It reflects a lot of sunlight. So ice increases the albedo. Then, of course, clouds, they are also white. They reflect a lot of sunlight. They also increase the albedo.
Now I've jinxed it. This is the whole episode is just going to be about the Earth's libido now.
I think it's going to be a long-running joke in the pod. So the third thing that surprisingly affects the libido of the Earth is deserts. Because desert sand is relatively light colored, right? It's not dark. And surprisingly, because of that, it actually reflects a lot of the sun. So these are the things that increase the albedo. And then what decreases the albedo is things that are dark. So first of all, vegetation, especially forests, and also the open ocean. Water generally absorbs a lot of sunlight. So if you think about this a little bit, ice is definitely melting everywhere, but that happens relatively slowly, and we can measure it from satellites and estimate it. And let's say from the 0.5% reduction in the albedo, maybe 0.1 is due to ice. So a bit, but not that much. Deserts, we know that deserts are expanding because some places are getting more drier as the earth warms. But again, that's not such a fast process. It cannot contribute to this albedo change. Similarly, forests are still being cut down. So when you cut down a forest, what remains behind, the soil, and is usually lighter colored. So that could contribute to this albedo change. But again, on a planetary scale, it's not a big enough effect to be important. So what remains is clouds and water, clouds and oceans. It has to be somehow related to them. So what happens is either for some reason we have less clouds so that more of the ocean is exposed to the sun and it absorbs more energy, or the reflective properties of the clouds changes. They become less light, they become less bright for some reason. So this is where we need to look to find the explanation for this warming. So it's happening over the oceans and it has to do with clouds. The two major explanations that are being explored in the literature are something that you would call a climate cloud feedback, a feedback mechanism. It's a kind of change that happens because the Earth warms. When it reaches a certain threshold, it might be the case that a certain type of cloud either disappears and never forms and then leaves the ocean exposed, or like it moves to higher altitudes, to whatever, around the globe. So it's something changes in the cloud pattern. Now, this would be surprising because it would be a phenomenon which is not captured in current models. And yeah, it would be surprising, but it's one of the possible explanations. And the other one has to do with aerosols and the way specifically that aerosols affect clouds and the properties of clouds. And this is the option that we are going to explore in this episode.
Okay, so what are aerosols? Is that how you pronounce it? Aerosols? What are aerosols?
I don't think I'm the right person to ask. Aerosols. I say aerosols.
Okay.
It's always a mystery to me how people pronounce stuff. We mentioned Hansen a lot. He always says, instead of measurement, like he has very good English, he's American, but he says measurement in a very weird way. And it's baffling. Anyway.
I think, yeah, with our Eastern European accents, we're just going to say whatever comes out.
Yes, this podcast supports Balkan English.
Okay, so what are these aerosols?
Yeah. So in a nutshell, they're tiny particles that are suspended in the air, that are transported in the air. There are many types. For example, desert sand, when it's taken up by the wind and it's transported across maybe to southern Europe or even to Florida, across the Atlantic, then we call it an aerosol. That's an example of a solid particle aerosol. A lot of other types of aerosols are liquid droplets in the air, and they form especially from different types of polluting gases that are emitted when you have different kind of burnings, either burning of biomass or burning of fossil fuels. And those release a lot of stuff. They release CO2, but they also release sulfur dioxide. They also release soot. Soot is also an aerosol when it's suspended in the air. It's a solid particle. It's a clump of carbon atoms, right? And so all of these particles together, collectively, are called aerosols.
So basically, aerosols is just a sort of like a name for really tiny things in the air that can be anything.
Yeah, exactly. And to make the tiny more precise, it's something that's a few micrometers in diameter, somewhere between the width of a human hair and much larger than individual atoms. So it's kind of in the middle scale, not visible with the naked eye, but also not as small as atoms.
So basically, we also breathe these things, and some of them are bad for our health and some are good.
Yeah. So aerosols actually have a huge health impact. I think we should come back to this as we start exploring what aerosols are. But for now, let's just say that of all these different types of aerosols, we are really interested in the ones that contain sulfur. And that is because these ones reflect sunlight. Some of the other ones absorb a lot of sunlight. These have the property of reflecting a lot of sunlight. They also have a strong impact when they interact with clouds. So what is the source of these aerosols? Well, basically low-quality fuels, meaning coal and oil, they can contain sulfur. It's like between 1% and 4% or something like that. So when you burn the coal or the oil, then that releases, as I said, along with CO2 and other pollutants like soot and other stuff, it also releases sulfur dioxide, SO2. That's a gas, so it floats up in the air. And when it encounters water droplets, water vapor, then it turns into sulfuric acid. It's kind of surprising that this acid that we learned, that it's one of the strongest acids, right? We learned in high school.
Some people learn that.
Yeah. I think most people learned it, but only some of them remember.
Yeah, maybe some people heard it if they went to class.
Yeah. But yeah, so it's surprising that this very strong acid is actually present in the atmosphere in quite a lot of quantity. And it forms this kind of droplets, tiny droplets that are smaller than rain droplets, right? Because rain is heavy and falls out of the air. So these are smaller than rain and can float in the air for a long time. And as they float in the air, they draw more water, and they also attract different kinds of pollutants, ammonia and other stuff, salts, organic compounds maybe. And all of those stick onto it and get dissolved into it and form these particles, which we call aerosols. And so those are the ones that are interesting for us from the climate perspective. They reflect sunlight and so have a net cooling effect, which is surprising maybe because they're also pollutants.
So it's like they are bad. They are bad, but they're also good.
Yeah, they are very bad, but they have this positive side effect. But the side effect cannot compensate for how bad their impact otherwise is.
Yeah, unredeemable villains.
Unredeemable villains, yes, with some positive traits, exactly. Yeah. So to explore a bit the role of aerosols in the climate, let's look at how temperature changed during the 20th century. There was an interesting period during the 50s and 60s where in the scientific community an understanding of climate change was developing, and everyone agreed that a rise in CO2 would warm the atmosphere. And CO2 was rising, it was started to be measured. However, during these 2 decades, the temperature seemed to stay in place. It was not rising. So it was kind of weird because as scientists recognized the danger of climate change, the temperatures were actually not rising. And so it was a conundrum. It was very bizarre what was happening, right? But in the meantime, during this period, the phenomenon of urban smog and of acid rain were becoming more and more of an issue. So in the US especially, they started studying it very closely. Scientists realized during the 50s that this effect, both the smog and the acid rain, had a lot to do with sulfur emissions and these sulfur aerosols that form in the atmosphere. So this sulfur was contributing to the smog and this acid rain. And also, of course, when people inhale these aerosols, it had a bad impact on health. Even today, maybe not a lot of people know this, but today aerosols and other types of air pollution, of course, they are one of the leading causes of death globally, comparable to cancer. It's still incredible. It's like something like 5, 6, 7, 8 million people die each year because of air pollution. It's
a lot.
Yeah. So yeah, there was growing recognition of the role of the sulfur aerosols, but at this time it was mostly in its contribution to smog and acid rain, right? So that was harming people's health. It was harming crops, right? Agricultural production. So we needed to cut the emissions. So during the 70s in the US and in Europe, mostly in Western Europe, a set of very strong regulations was introduced that led to the drop in sulfur emissions. When we look at the temperature, not surprisingly, after the sulfur emissions dropped, the temperature started to increase. It was like a very sharp turn in the 70s when the global temperature started going up. And as we understand this today, this was because, as we said before, this villain, the sulfur aerosols, while they did a lot of negative stuff, they also had this effect of cooling. And that cooling kept the warming that was due to CO2, it kept it in check. During these 50s, 60s, they kind of canceled each other. And so when the sulfur was removed or reduced, then the warming due to CO2, it was unleashed. It was no longer kept in leash by the sulfur emissions.
So just to be clear, basically they did this by forming clouds, certain clouds that would affect the Earth's albedo.
Well, these aerosols have two ways of influencing the radiation. First of all, these droplets themselves, they reflect more sunlight. So there is a direct effect. And they also have an indirect effect on clouds, yes, as you said. So when you have an area of very high concentration of these aerosols and the cloud moves through that area, it incorporates the aerosols in itself. And it has a very interesting effect. When rain forms, in order for droplets to form in the cloud, you need something onto which the droplets need to condensate. It's called the cloud nuclei. That could be different things, but generally it's some kind of aerosols. So every rain particle, every rain droplet that falls to the ground actually has some kind of aerosol particle in its center that started the condensation process. But rain can form even like with a very low levels of background aerosols that always exist in the air, right? But if you have an injection of these lots of aerosols, then something interesting happens. Instead of forming large raindrops, you form lots of little drops in the cloud because there are more condensation nuclei. That has different effects, but the most important is that it makes the clouds brighter, meaning that they reflect more sunlight. And so more aerosols lead to brighter clouds, and brighter clouds overall leads to an increase in albedo.
Is this how people got the idea of geoengineering? They looked at these things and they said, well, we could do that. We could make clouds brighter.
That is exactly 100% where the idea of geoengineering comes from. There are two examples in nature, right? One is that when volcanoes erupt, they blow these kind of sulfur aerosols into the stratosphere, and then they form these droplets of sulfuric acid there, and they stay there for a long while in the stratosphere. And that leads to these large cooling events after each volcanic eruption. That's a known thing. So that is one type of geoengineering, to push sulfur aerosols into the stratosphere. And the other one is like this, to somehow sprinkle some aerosols onto low-level clouds and change their brightness. So these are the two main types of radiation management type of geoengineering. So yeah, it's 100% where it comes from.
People thought, well, we did this bad thing and it kind of worked like this, so I guess we could do it again and maybe it will work better.
Exactly, yeah. Well, the idea is to do it in some place where it would not affect people, but that's not a real thing. Everywhere you put it, it will affect people. We will maybe have an episode about geoengineering, but it's...
It's a lot, yeah. We should, yeah. Let's get back
on track. So during the 70s, 80s, up to 2010, we had this almost linear increase in the temperature of, as I said, 0.18 degrees per decade. And initially, they thought that it is because the sulfur was completely removed from the atmosphere, right? After the Western countries imposed these regulations. However, as emissions from the Western countries decreased, China was industrializing heavily in the 80s and 90s, right? And so their sulfur emissions increased. So actually, during this period of 1970 up to 2010, it seems that this linear trend of temperature was due to the fact that this decrease from the West was compensated by an increase by China, and they overall led to a kind of constant level of aerosols, a constant impact. So it was like sulfur emissions were holding back the CO2 with two leashes, and in the 70s, one of them was taken off, but one was kept here until 2010, 2015, when something else changed. I don't know if that was clear.
Yeah, so it was like the US and Europe, they were like, we're not going to put this bad aerosol into the air anymore because it's killing people. But there was industrialization in China and it kept being put in the air in one part of the world, right? And then at some point they were like, we're also stopping now. And then everybody sort of started stopping, and then bam.
Exactly. The BAM is the accelerated warming. But just to take it one step at a time. So during this period of 70s up to the 2010s, even though in some places it was increasing, in some places it was decreasing, kind of the effect of aerosols, of holding back the warming, was kind of constant. It was much less than in the 50s and 60s, right? Because temperatures were rising, but it was still there. After 2010 or maybe 2015, we start observing a weird kind of behavior of the temperature. As we described in the previous episode, the temperature starts jumping very high from year to year, especially in 2023. It had a huge jump of around 0.4 Celsius. And all of the people from IPCC and a lot of the researchers working on climate models were baffled because this jump could not be explained by their models. And maybe here to make a small aside about climate models. So climate models are these huge giant machines that require a lot of computing power. So not everyone can make their own model. There are like 30, 40 models around the globe. And there is a project called CMAP that kind of gathers data from all of these models. And so IPCC uses this collection, this repository of model simulations from these 30, 40 models around the globe to produce their simulations, right? And so what happened in this 2022 jump was that none of these models could explain exactly what caused this jump. These models are actually very good at explaining the variability of temperature during the last century, let's say. Like if you look at a plot, the temperature has a trend, but then it goes up and down quite a lot from year to year, right? Well, that jumping up and down can be explained mostly by volcanoes, the El Niño phenomenon, and other types of internal variability of the Earth system, and then anthropogenic sources like CO2, methane, and other greenhouse gases, and aerosols. Basically, these are the main drivers of the climate. And if the modelers put all of the information of all of these together, the models actually can reproduce quite well not only the trend of the temperature, but even the jumping of up and down from year to year. So you would expect the models to explain quite well even this high jump, and they cannot. Half of it is explained by a large El Nino in 2023, but the rest is a mystery. No one could explain it. There's one paper in Nature, I think by some researcher named Schmidt, who was saying that this means that something really new is happening and which is not captured by models. It was kind of a surprise thing and kind of a crisis almost that models cannot explain this jump. So there's a mystery.
Is this a detective story now?
Yeah, I tried to frame it from the beginning as a kind of a detective story with the albedo, and I don't know how well it worked, but yeah, it's kind of a detective story, right?
So people were like, who is at fault? Who did this?
Yeah, so it's a whodunit mystery story. And the IPCC says that it cannot explain it. We know that it has to do with the oceans, especially some changes in the properties of clouds above these oceans, especially in the North Atlantic, the North Pacific. But it's still not clear what is producing this effect. So we said that we are going to focus on one explanation that is due to these aerosols, and especially the indirect effect of aerosols.
So this is one theory, you mean?
Yeah.
So we have one culprit. Some people think this is the culprit. We will explore it.
Exactly. Well, actually, if you look at the papers that study this jump and this period, even if they don't give an explanation, most say that the two basic explanations are the one that I gave in the beginning. Either something changed in the properties of clouds due to the temperature rising, which is not captured by these models, or the effect of aerosols. Most people say that it's one of these culprits, right? That's what I'm trying to say.
So we only have two culprits to look at. Amazing. It's not even that complicated.
Well, so others say other stuff, but these are the main culprits. Of course, the people that are saying that it has to do with aerosols are J Hansen and the leading researchers that publish papers together with him, because that's why this whole discussion is tied to Hansen.
Okay, so let's look at the evidence, right? What did they find?
So what is clear, we need to have something major happen during this period that would cause these jumps. And if you look at CO2, if you look at methane, if you look at, I don't know, circulation in the ocean, if you look at, there's nothing, there's no giant collapse of ice somewhere that would cause this. And so you eliminate all of the probable causes, and then you need to explore improbable causes, possible but improbable causes, right? So one thing that happened during the last 20 years was that the sulfur aerosol emissions that remained were drastically cut. And this happened from two reasons. First of all, China introduced pretty strict air quality legislation in 2010. I'm not sure exactly when the year was, but it was pretty successful. The stereotype is that in a city in China, you cannot see the sky. It's full of smog and stuff, and you cannot see the sun or the sky, right? And that's no longer true. The air quality is still bad, but they reduced all types of air pollution very, very drastically in 10 years. That includes aerosols. So that is one contributor. And the other, an unlikely culprit, let's say, is emissions coming from international shipping. Shipping means transport of cargo. That includes transport of fossil fuels, of course. This factor has not been seriously considered by other people besides Hansen's group before, because in general, as a percentage of global emissions, the shipping industry has like a small percent, I don't know, smaller than 10%, I think. So it's something small, and no one would expect it to have such a big impact.
Okay, so why did they look at it?
Why they looked at it is because the jump happened in 2020s, right? And the shipping industry, the International Maritime Organization, actually introduced a law or regulation in 2020, which made all the ships use fuel that has very low sulfur. So their emissions dropped drastically, very, very fast in 2 years. And it looks like it's the only thing that changed very drastically during these years that could possibly be linked to this high jump in temperature. So that was the initial clue for it. And then as people started exploring this issue, it seems now that it could be the culprit. So what happens is you can actually see in images that where the major shipping lanes are, where ships go back and forth, especially images from before 2020, you can actually see clouds either forming or getting brighter on those lines where the tracks are. You can see the shipping lanes from images of clouds. It's amazing. It's like the tracks you see being produced by airplanes, right? Similar in aspect. But these are actually new clouds that are forming or clouds that are getting brighter. They're not just some water vapor like is produced by airplanes, because that dissipates very fast. But these are clouds that persist and have these changed properties. So, yeah, Hansen's explanation basically is that even though these emissions are low, or were low, even before 2020, compared to the total global emissions, but they happened over the oceans, which had very little pollution before. And even these low numbers of aerosols were enough to impact the clouds very strongly. There is kind of saturation effect. In very polluted environments, aerosols start impacting the clouds, and after a certain point, the impact no longer grows. You have a saturation, right? And so the strongest impact is exactly when you go from zero to a little bit of aerosols, right? And this is their explanation. Even though you have relatively low emissions globally, but it happens in a pristine environment above the oceans. And because where there was none, now you are injecting these aerosols, then it can actually have a strong effect on clouds. So basically, their explanation is that this aerosol effect on clouds disappeared after 2020, and it disappeared very fast in 1-2 years. And this led to this jump. There were less clouds, so the ocean was exposed and absorbed more heat. And also the clouds lost their brightness, which was due to these aerosols.
That's so fascinating. How could people not see it before?
Because it just seemed like too small of an effect. In terms of total percentage of emissions, it seemed just too small to have this big impact on climate. But it's happening exactly in this time after 2020, right, when these big jumps occur. And it also happens exactly where the increase in the temperature appears, in the North Atlantic and the North Pacific, and also the rest of the oceans. But shipping traffic is largest exactly in the North Atlantic, where we see the most extreme heating. So all clues point to this, although it's still not fully accepted in the literature that this is the explanation, but it's starting to talk about it and study it more. So yeah, that's the bottom line. Like in the analogy, aerosols, due to their cooling effect, in the 50s and 60s was keeping CO2 in check with two leashes. I don't know if this is a good analogy, but anyway, it's keeping CO2 with two leashes. And in the 70s, they took one off because aerosols started dropping a bit. And then in 2020, as these shipping emissions were cut, the other leash was taken off. And now we see the full force, the full unchained global warming potential of CO2 and other greenhouse gases.
Yeah, that's a strong image.
And again, this explanation is not yet accepted in the literature by everyone. But if this is true, if this is the cause, that aerosols are causing this acceleration, then we expect that after a transitional period, the warming trend will stabilize somewhere closer to the current trend. In any case, much higher than the previous trend from the previous decades. And what that means is that probably purely because of this effect, all of the IPCC's projections will need to be revised upwards. The same emissions will lead to higher warming.
Okay, so it's bad news, in short.
Yeah, it's bad news. Did you expect anything else from me?
Always bad news and bad news. But wait. I have a question. So we're saying with this theory that the culprit for the sudden change in warming trends is the aerosols, right?
Mm-hmm.
So if it were like the other culprit, would it be better news?
I don't know exactly the implications of that. It might be that after this period, the trend continues like before, but I'm not sure. I haven't actually read about it and I don't know, to be honest.
See, we need to explore that as well.
We can explore that as well, of course, yeah, in a different episode. And I think we will just leave you with a teaser for the next episode. It's interesting, if aerosols are the culprit for the current accelerated warming, it also means that the warming effect of CO2 is also underestimated. Because if you change only the aerosols, then we would not be able to explain the temperature during the 70s, 80s, right? That stable increase. And so the only explanation would be if the warming potential of greenhouse gases was actually larger and the two compensated. Underestimation of cooling from aerosols and underestimation of warming from CO2. And of course, that has huge impacts. There is one parameter that captures this warming potential of CO2. It's called the climate sensitivity. And it is one major point of research to actually determine what is the climate sensitivity of the Earth. And that is what we will be talking about in the next episode.
I like the term climate sensitivity. I don't know what it is exactly, but I'm looking forward. So thank you for being with us through this strange, terrible story that turned from erotica to detective to horror, the climate genre par excellence.
Yeah.
This is not an ad, because we don't have ads. This is a fully listener-supported podcast, so please support us if you can. So, we've been talking about the Earth's albedo, but let's reconsider the Earth's libido. For today's offering, I want us to get back to that idea. I mean, it is quite a huge metaphor, but we can give it a try. Because it does raise the question of our exploitative relationship to nature from a different viewpoint, one we may have not yet considered. We more often tend to talk about the earth as a mother, the earth as an entity that cares for us, does things for us, and we take and take until we end up destroying even earth's capacity to give. What if a different image comes to mind? The image of earth as a lover? This is what the queer ecosexual artists Elizabeth Stephens and Annie Sprinkle proposed sometime in the 2000s. For them, this way of relating and making art can be a radical form of environmental activism because it invites people to consider nature as a partner, someone to give back to. Nature then is not something, nor someone who you're supposed to have power over. See how this mode of relating that is queer intrinsically criticizes patriarchy as well as capitalism. But Sprinkle and Stephens don't take it too seriously. They probably know how absurd it can sound to caress rocks and be pleasured by waterfalls to some people. Others will find it very enjoyable, I'm sure. But see, humor here plays a big part. In the midst of immense climate grief and rightful anger, both which can consume us to the brink, the powers of the erotic, the joyful, and the humorous can nourish us back to life, back to a point of strength from which we can fight for the rest of nature. We can struggle for mountains and rivers and forests, for oceans and deserts and marshlands, because we love them. Not only for that reason, but love certainly will give us strength. In the ecosexual manifesto, Stephens and Sprinkle wrote, "The earth is our lover. We are madly, passionately, and fiercely in love, and we are grateful for this relationship each and every day. In order to create a more mutual and sustainable relationship with the earth, we collaborate with nature. We treat the earth with kindness, respect, and affection." So then, considering Earth's libido is a light-hearted way of asking, can the Earth still love us back after what we've done and continue to do? It asks us to step back and wonder just how badly we've affected the capacities of natural entities to regenerate. Are we bad lovers? Can we stop? Can we change? To begin an answer, I want to offer a song called Eroterra. It is the last track from the superb album Ecotranarchy by queer artist Sofia Zadar from Romania. Their music often searches for imaginaries beyond the Anthropocene, drawing inspiration from non-human entities. Here it goes.
Your skin now, watch you breathing. I wanna worship every move you make, but I don't think I'm worthy of your time. 'Cause darling, I can't love you right. No matter how I try, I can't undo it. I hurt you with my every single turn. 'Cause honey, I was made to do you wrong. I don't know why I can't love you right. body, my rock body, my lava body, my plant body, my symbiont body, my compost body, my celial body, my body, my body, my dirt body, my moist body, my ice body, my liquid body, my sand body, my animal body, my plankton body, microbial body, my body, my body. We still live as one, I can still feel it. A single being locked to separate parts. The lover I was taken from your arms before my time. And now I can love you right. Sun to my right, moon to my left, sea under my feet, sky above my head. Sun to my right, moon to my left, ground below my feet, sky above my head. Sun to my right, moon to my left, sea under my feet, sky above my head. Sun to my right, moon to my left, ground below my feet, sky above my head. We've been slaughtering nature to prove God is dead, so the mightiest humans can play God instead. Shells glitter and glow in the frosty November sand. The sun plays God, and I do believe they're the best that I've seen in this part. The witness I feel when I witness your brightness is more than I need to embody my purpose, cause I know as long as there's sun to my right, moon to my left, ground below my feet, and sky above my head, I will work for a world that has gifted me such love.
Thank you for listening to The Last Fireflies. We're a small autonomous group and we're listener supported. So if you can contribute to our Patreon, please do. This money will go to support the work we are doing on this podcast and keep it going. But not only. After we reach a certain threshold, we aim to try to distribute it so as to help grow the climate movement in Romania and then maybe even further in a bigger network in the Balkans and Eastern Europe. Thanks so much.